Well, hello everybody. I am starting space weather classes again tomorrow. So I'm kind of gearing up by reviewing my final from last semester. It was nice I got an A, but not an A plus. So there's a few things that I definitely need to understand a little better before I hop into learning even more in-depth information. And some of this affects you. All of it affects all of us, but there's some people that I know have more of an interest in learning some of what's going on here. So I just wanted to share what I've learned so far and kind of go over this. I thought it would help me get through my work if, I did this in a sharing effort here. Because I had told some people that I would share this information and let them know what I was learning. So here we have what is called SWEN, a space weather. This is a new program out of Millersville University, and somebody named Space Weather Woman, Tamitha Scove, started this. Before I even made my Weather Woman page, I had been following her, not knowing she even went under that name, and I thought it was so funny. I have so many similar interests to her, but she's well ahead of me as far as the academics are concerned, and now she's my professor. So I'm glad she spearheaded this program and started bringing us all more information in a public spectrum on her YouTube and then making it available at the collegiate level as well. So that's what I'm studying now after my bachelor's in meteorology. So looking through here, I'm just going to kind of go through the basics real quick, just reading this out loud, and so you can kind of have an idea of what's up to come in case you don't want to hear everything but want to look ahead for a specific portion of this. Here's a little overview of what we'll be looking at. So I'm going to kind of dig into data sources that are on satellites, institute satellite data, looking into how it affects our radio communications. What are these magnetic bands on the sun and why that plasma matters and how it can leave the sun and affect Earth, or why it might leave the sun and not affect Earth. What kind of radio bursts we have and why. As you can see, I could use a little extra help on that. I messed up the question, says my professor. So there, it's funny. We're all subject to error, humans, even computers. And then on top of that, we'll be looking at different, like I was saying, how something could leave the sun and not affect Earth. This is the hows and whys of that. What is the heliospheric current belt? On my Weather Woman page on Facebook, I just posted about this. We've just happened to go through a fold in this heliospheric current sheet, and that affected some amazing skies in Finland. They had green aurora because of it. Here, well, we'll dig into that later, 0 points, but more about these streamlines and heliospheric current information. We have stuff here, again, a lot of heliospheric information still, and then more of it. It's a big deal. So that is it. Oh, and then of course, fun stuff here with the, what's being called Astro Sociology. Is what the end essays are about, and that's basically just information about how all of this is affecting people and how we can come together. There's a new journal, an Astro Sociology journal that reviews the hows and whys of mitigation, and just it's really interesting. This journal only began in 2015, so this is all very new information, and I'm excited to be able to share some of it. And my big reason for doing this before I get started, just so you know, is because as I was studying meteorology, a friend of mine, a dear friend, thank you, Doug Tanner, he got me hip to Tamitha Scove's YouTube page. That's TAMITHASKOV if you're interested. And a lot of information she was sharing was like over my head, but I did notice some correlations that when she was calling out these big plasma ejections from the sun, the CMEs are leaving the sun, and I was busy studying hurricanes and forecasting for hurricanes, rapid intensification was occurring that was not being caught by the model forecasts. So I decided that there must be some kind of correlation. I also saw that there were correlations between space data and lightning forecasting, and that now is operational, just started this year. That's something you can find on NOAA, NCEP, all of the NCEP, if you want to look up those models online. We now have a lightning forecast part of the HRRR, the HRRR model. And it's pretty incredible, if you ask me, that these things are being studied to the degree that they are. So we're going to have rapid changes and enhancement of our models because of this information. So I feel like the more people that know this, the faster we can achieve more long-term accurate forecasts and be better prepared for the weather and mitigate more effectively. So I'm reading through this starting now, enjoying a little bit of refresher before my classes start tomorrow. So CMEs and ICMEs. These are coronal mass ejections and interplanetary coronal mass ejections. So the ones inside our solar system from our star and our sun are the CMEs. And outside of our solar system, we can also intake some of these energy sources and plasma outbursts. It says, what is the difference between a gas and a plasma? A collisional plasma and a collisionless plasma. Explain. So we have a plasma forms from ionization of gas. That means it's being charged. Gas is considered to be comprised of neutral atoms, can form ions by gaining or losing electrons, respectively forming a negative or positive charge. The difference is that plasma is an ionized gas in a higher energy state with free electrons and ions. If collisionless, the particles are more spread out and not interacting with one another frequently. Things collide less, collisionless. So in this case, in outer space, particles are oftentimes further apart from one another, whereas inside of our magnetosphere and part of the Earth, or part of the big chunk of plasma that gets ejected from the sun sometimes, that's going to be collision, there's going to be a lot of collisions going on in there with these little particles. They can be charged or not charged. And so if it's charged, that's ionized. CMEs can result in what? Well, so these coronal mass ejections can cause interplanetary shock waves. They can cause radio bursts. Anybody who uses the communications on the radio frequencies, like my husband does for work, or a lot of amateur radio propagators use, and military uses this a lot, it's going to affect it. It's something that not too long ago people would be perplexed about, working, wondering why their equipment isn't working, tearing things apart, trying to fix it, when really it was all space weather related. And if they just waited a certain amount of time that now we have the data collected for, we already know ahead of time, okay, wait 15 minutes, wait a day and a half, wait for these fast solar wind streams to go all the way around the sun. Sometimes even maybe 2 weeks, things will be a little on and off with radio communications. So we can also get aurora, the aurora borealis, or spacing on the other name right now for the aurora in the southern hemisphere, but that one helps light up the sky with ionized particles. And also we can get radiation storms. And we'll dig into that a little bit more here in this same text. And then she says, can it cause coronavirus? There's a little humor in here. And I say we may need to cross-reference disciplines to answer that effectively. Who knows? But for all I know, with people working in the medical field, UV light is actually used to kill viruses in hospitals and sanitize. So there's a lot that our sun does to protect us against viruses if we're in it. And of course, high amounts of radiation can also cause cellular DNA changes. And just how much we're getting and what other input we have in our body may or may not make the sun damaging to us. So we have here, what is a halo CME? Now I got that wrong a little bit, and I checked it out again because she wanted me to get more that she's looking for that the CME, the coronal mass ejection, has a signature ring or halo 360 degrees around the sun in coronagraphs. There's certain wavelengths of light that we look at for different types of phenomenon on the sun. Some will eliminate different wavelengths, like gamma ray or X-ray, while others will increase the view of that particular type of element. And so in this case, we can see the sun and it looks like a black disk, and on the outside we might see some colorful bursts outward. That is what it is. If there was something so powerful, it'll light up the sky behind it in a specific angstrom or wavelength of view. So these are CMEs that move directly toward or away from the location of that coronagraph. I've never used this in this way, so here we go. Let me go back. How can an EIT wave help determine the size and extent of a solar storm as it is launched from the sun? So we have SOHO is one option for EIT waves to be sampled. The duration and velocity of measurable particles can aid in forecasting solar storm severity. She says we can also tell from the wave how wide in longitude or latitude the CME will extend. That has a lot to do with whether or not it will touch Earth's magnetosphere or not. And EIT waves are I'm trying to remember right now exactly, extraterrestrial, interplanetary. I'm going to look that one up because this is the reason I'm reviewing, making sure I'm all ready for next semester. So EIT waves. I'll take a moment to find this in my book and be sure I know what exactly it's made to define. Not finding it in the book. Amazing book, by the way, Eloquent Science. Oh, goodness. If you write, if you broadcast, or if you're studying weather, it was written by somebody who's on the board for the a meteorology journal, and it was incredible. So I do definitely have EIT waves mentioned in my notebook. Fun stuff here. So many memories of last semester coming back looking at this. And the EIT waves came up somewhere in the middle of the class here. So where are you? And in the event that you are bored here with me, if you're watching live, I plan to later on when I get extra time to go back and chop this up to make it a little quicker and easier to follow along with. And edit in some of the imagery so that you can understand exactly what I mean by saying things like that radio, like the radio bursts, exactly how they look and all that.
I'm in the store.
Hi, okay, cool. What store are you going to?
The store that sells hopefully grills so I can barbecue since it's a long way to cook.
That sounds good, thanks. What is an EIT wave? Do you know?
What's up?
What's an EIT wave?
EIT wave?
Extra. I'm going to look it up on the internet since I'm not finding it in my notes really fast.
Yeah, I don't know.
Yeah.
I love you.
Why would you? I love you too.
You need anything? I'm gonna get Black Beast.
No thanks. That sounds good. So, EIT waves, what are they? Here we go. That's interesting. Geez, how weird that this is. I'm finding a bunch of different sources here talking about EIT waves, but they also are not writing out what it means. Well, what does it mean? It says it best describes fast mode large amplitude waves or shocks that are initially driven by the impulsive expansion of an erupting coronal mass ejection. But yeah, I'm trying to remember because I like to go off of nomenclature to really plug things in my head. And it's so weird, like I'm not finding what it means, but it's capital EIT wave. So I'll probably just move on from that and say I'll figure it out soon enough. But so you can get an idea of what old school coronagraphs used to look like. Here's one. So you can turn off certain wavelengths, pick up one wavelength of light, and then capture the outside area and notice that there's a halo around. So in that case, that means it's moving toward or away from the sun. Now, onward. Well, SOHO, I'll go over the answer there. So, the EIT wave, SOHO is one option for EIT waves to be sampled. And what that is a satellite that's out in space between us on Earth and the sun. So, they're getting information and can sample parts of that plasma or that shock wave. And it will tell us, yeah, how strong is it? How much will it affect aurora chance or radio communications? Now here we have right hand rule stuff. If you've ever studied meteorology, dynamics, or anything like that, we use a right hand rule situation, and that's what this stuff is. This is a time series data for a stealthy ICME that hit Earth in late April. I showed the beginning of this event in class on 420. However, the flux rope was anomalously large for a stealth event. I expected it to be a much shorter duration. So I got the flux rope prediction wrong during the lecture. Assuming the flux rope is bounded by the vertical dashed lines, which is the proper orientation according to the flux rope, leading field, axial field, and trailing field. So assuming GSE coordinates, she wanted to know which this was. And this one was a little tricky for me. Sometimes they're straightforward, and the way that I notated it in my notes, I had it put pretty simply, and this one just got a little tricky. So there was a specific series to know if they're coming from the north or the west or the south. It's basically saying, is this rolling through space coming this way, or is it rolling through space coming this way, or is it vertical this way or vertical that way? And it matters a lot because half of those orientations will not connect with our magnetic field. So no matter how hard they hit, even if it's what's called a Carrington event, X-class flares, huge, powerful things, if it can't connect with our magnetosphere, it will not affect it. It will just keep going by as strong as it is. So this is a very important piece to the puzzle of understanding what's going on here. And then when I go ahead and I'm going to make a note here verbally to cut a snippet out of this and then add in imagery of those different axial fields. And, in class I can get pretty sloppy. And if this is backwards, I'll just edit it to make it right again later. But you can see they might be vertical, or they might be, coming in east-west or rolling down. And this is how the right-hand rule works. So I made a little note here on which is the leading, which is the trailing, with the right hand or the left hand for the axial field, these flux ropes, and exactly what's going to be negative or positive or positive. So what I did here to make my mistake was that there's a BZ and a BY field, and I was kind of mixing them up. And typically B or Y is the meridional field, and that'll go kind of like a sideways projection through space, whereas our X fields go along flat along a horizon, and then the BZ is going to be the up and down portion of this, like if we were looking up to the sky, and meridional outward, x plane is just straight across. So with that, I'll add in, how the positives and negatives work. But with this particular answer, I just mixed up the colors. So we have the east being coming in here first. We have a west that we're looking at the beginning here. So I used the wrong time code too when I was interpreting this. So I have a time in and a time out for this flux rope passing the instrument. So when the flux rope began to interact with the instrument in space, the instrument noticed that it was higher up, a positive number on this east field. And then that when it was leaving, the westerly flux rope was there. So then we have a north one on the up and down axes. So this is going to be ENW. And I'll just go ahead and put a nice graphic together to explain a little bit more of what that means and how it can matter. I think that it'd be better not to do it right now, but what I'll do then is show exactly which kinds of flux ropes would connect with Earth and which ones wouldn't, because that's going to be a big deal when you hear somebody talking about a possible Carrington event or something. So true or false, the frequency of radio burst emission increases as the location of that source increases in altitude within the solar corona. So that's false. So what happens is that frequency of how much a wave is going up and down over a certain period of time, it's actually going to decrease as you go up in latitude with the solar corona or the sun. So if we're at the equator of the sun and then we start moving up, we notice that the frequency decreases toward the poles. And here's the fun stuff. This has beautiful imagery to go along with it that real quick I'll put in here, and then later I'll also edit in some better imagery because this is one of the prettiest things. This is one type of solar phenomena, and it's part of the picture I chose. So this is actual plasma leaving the sun, coronal mass ejections, mass from the sun, blowing off, coming right toward us sometimes going away from us. And again, these magnetic field orientations have everything to do with whether or not they actually bother us here. So label each of these standard flare and CME model diagrams. There's a lot of pieces to the puzzle here, so I'm glad I got them all right, and this is a big deal to remember for me. So I do remember this is the X line off the top of my head. We have a foot point here. Magnetic reconnection line is also called the X line. So sometimes there's different looking models, and she wanted to make sure that we knew how to view these in different studies, different books, and still understand what they mean. So there's a couple different things here, but it's actually all the same information. So first we have these foot points on the sun. This part here that's kind of on the bottom here, it's called a flare ribbon because the sun is moving around in a circle also like our Earth. And as that happens, there's little parts of this foot point. The foot point might be here, then it might be here. And there's also underneath, inside of the plasma on the surface of the sun, there are these extra sources called flare ribbons. And from these foot points, we can have a positive and a negative polarity connecting to one another that actually is protruding from the sun. And you can view these on Space Weather Live or on the Space Weather Prediction Center in real time and see what the sun is looking like now. And in those specific wavelengths of light, you'll be able to see that, yes, in fact, it's bulging up and down. And then every now and then, the plasma ejects. And when it ejects, there's a specific point that will snap up and go out, and another point that will snap back down into the sun. And those can cause their own shock waves, and in between that is called the X line, where we then have magnetic reconfiguration. So beyond that, there are these, I want to say this is the flux rope. Did I remember it? Yes. Okay, good. So these are the flux ropes. And then on the other diagram, we see the purple flux. This is the flux rope here. Kind of looks like this CME part, so that's why it can get confusing. But really, foot points and flare ribbons connect those parts. And this would be the magnetic reconnection, or X line here. And then sometimes we have these open solar wind streams, an open flux that is going right up and out to interplanetary space, or maybe even toward Earth. So besides that, we have the hot flare loop. Let me see, I didn't cover that one yet. So yeah, the hot flare loop. I just was talking about it, but the technical term for this region that's connecting positive and negative, or maybe it's positive here and negative there. More reason to know hows and whys of that with solar cycles. But that will change from the southern and the northern hemisphere with time. About every 11 years to 14 years, we see that the positives go from one side to the other, according to hemisphere. So beyond that, with this, she wanted to know the source region for a hard X-ray emission is here at the foot points. Where we get the soft X-ray emissions is near these hot loops. And then just the source region of microwave emissions. So microwave emissions come just above the hot flare loop, up here and up here. And then the source region for type 2 emission would be above the X line. So just up here, or just right up here. That's a different type of radio burst. And on another page here, we'll see what those mean. It was actually one of my struggles learning this part, so I will pay an extra attention here. Here we see, we're looking at space data here, and these mean different things. You know, if the instrument is recording the radio burst, and it looks like this, very up and down, kind of short, high frequency, then it's the type 3. I have more to learn on reading this, so there is actually, you can see, well, I'll go with X and Y axes here. The Y axis says the frequency in megahertz. So these frequencies can reach high amounts, but it's not very wide. There's not a lot of meat to that. It's going up and down really fast. Whereas over here, we are getting frequency emissions just in different zones rather than all the way up and down. Some of them are actually stronger though and more congregated, and type 3 and type 3 for both of those. So that I messed up on the test, but now I better plug it in my head. And since she messed that up, she says free credit, but just because it's supposed to say type 2 and type 3. If both of these are observed during a solar flare, it indicates that a CME was launched with a shock wave. So one of these helps drive shock waves, and another type is always there with the CME. But not every CME is going to have a shock wave. So that's why this type of data can help us and can be important. I wonder if I have these notes, because there was a little more I'd like to throw in there. And if it takes too long to find, I'll just do that as part of an edit here. Here we go. So, types of radio bursts, because there are more. There's actually 4 indicated here in my notes. We have that the type 1 is between 100 and 300 megahertz. We have the type 2 are broadband, so that'll affect more radio transmissions in the kilohertz to 1 gigahertz range. About 500 megahertz decreases, it says. With the type 3, it's broadband travel into HF range, high frequency. And then in the type 4, we'll get both those two. So type 3 bursts, it says, are aka interplanetary. Another 5, it says, fades by lowered density gradually. So that's how you can kind of tell on these, how to read them. And I'll be learning more and more about what that means. For now, we've mostly focused on how that affects radio communications. When a solar flare occurs, how long does it take before its effects are observed at Earth? So solar flares can hit us at 8 minutes, but because they travel at the speed of light, and that's just how far it is from the sun. So when we know that the instrument says, hey, it's coming, there's not much time to prepare. Is important for events or people that need to have communications on all the time. We have Sunspots and Solar Dynamo here for the next section, and I'm going to keep having these lines in here. There was a funny edit when I handed in my test, so ignore those from this point on. She says, true or false, a sunspot can be dark in some frequencies of light but bright in others. And yes, most definitely. A sunspot lacks X-rays, and so in the X-ray wavelengths, it does not appear. It looks dark because it's not emitting noise in that frequency. But then in other frequencies, it'll be bright as can be. Now this is true. I got this one wrong. So it's true that the solar F10.7 radio flux comes from bright spots on the sun. The F10.7 radio flux does not come from a sunspot. So I had that in my head because of what I had just said, but there's different types, and this is what I really need to probably study a little more of before I start my next class. And now, defining Hale's law. How is it useful in assessing solar cycle variability? Is Hale's law ever violated? If so, how? So this was somebody who used to stare at the sun through a telescope a little more than 100 years ago, about 200 years ago, and helped us understand a lot about solar cycles, and that magnetic polarity, like I was saying, came in next. How it changes from back and forth on the north and southern hemispheres during different solar minimum moving into a maximum, and then back again. So that's a complete solar cycle when it goes from the minimum to the maximum and back within that small Mondrian 11 to 14 year cycle. And there's more cycles than that too. So I say that Hale's law states that polarity of sunspots is reversed from positive to negative, leading sunspots on either side of the equatorial region on an estimated 11-year cycle. I'm assuming I put next cycle. Violations or anti-Hale sunspots occur when the magnetic field structure of the dynamo is of a different orientation, appearing in a wave-like structure. So yeah, there will be times where there are some sunspots or different connections that don't quite match that solar cycle. And there's different reasons for that. She says they also happen more often with smaller spots. So I'll learn more about that variability, but it seems like sometimes the solar dynamo, what's underneath the surface of the sun, can be a little bit more sloppy during different portions of the cycle. Whereas other times it's pretty well defined, all negative, all positive, and nothing's ever completely one way that I've noticed with natural systems. So that's another indication of that being true. Now on to radiation storms. True or false? This is false now. Shock waves from solar storms reduce the impact of radiation storms. So they are independent of one another. The shock wave from a solar storm will not reduce the impact of a radiation storm. Those radiative particles, mostly protons that we have measured so far, they will still come through regardless of another shock wave. They're just going to travel through it. So in space, galactic cosmic rays are comprised primarily of relativistic protons. Relativistic that they are very high energy, more than what we would normally find here on Earth, but they can come into our Earth zone and affect us in different ways that I'll be learning more about soon. And this is not only collected out in outer space, but there are also areas on the Earth that keep records of these proton values. And I'll dig more into that later. Right now, she wants to know which radiation storm would reach Earth the quickest, and that's going to be something on the west limb of the sun. So, if you've seen my solar demonstrations or any of the forecasts I do on Facebook or YouTube, I've talked a lot about how if kind of need storms, if this were the sun, this little tiny ball here, then we're going to be looking at things on the west limb. So once the sun rotates, it's going in this sort of a direction, if we're thinking that we're on Earth right over here. Once the Parker spiral takes effect, magnetic connections, they're all going to be traveling in these circular ways. Because the sun is traveling in this direction, everything's kind of flowing around it. And the magnetic connections for Earth would have to wrap around in this sort of fashion to mingle with Earth's magnetosphere. Whereas if something were launched from over on this part of the sun, it'll kind of spiral around here, maybe go out toward Mars or whatever other, excuse me, Mars is right behind us most of the time, but there's different, different planets that may be affected by this sort of a launch, whereas Earth will not be when we're facing this way. And then these, what's on here for proton intensities, like I was saying, in space, they will test this information, have data collected, and we see different megavolts values coming out of these types of solar mass ejections, coronal mass ejections. And the quickest thing that would hit us would be right here if it's coming out of the west limb. Otherwise, something from back over here, even if it rotated around behind, if it's strong enough and the CME, the flux rope, all of that is wide enough, it could still branch into some of these field lines here and still affect Earth, but it would take more time for it to wrap around a little longer. And these are actual data sources. And so the way I answered that is when a storm associated with a solar flare that occurred near the west limb of the sun, it would affect Earth quickest. Now, from the Earth's perspective, which limb of the sun is best connected magnetically and why? And like I kind of just said, the west limb, because of the Parker spiral effect, it is most likely that relativistic particles leaving the sun via the west limb could collide with Earth's magnetosphere. Now, plasma, she says, careful. You mean relativistic particles. Plasma means slower moving solar wind. So plasma would have more weight to it, be moving slower. And she wanted to know magnetic connections and fast magnetic connections. So we could still magnetically connect with plasma, so she didn't dock me a point, but this is something I got to cram in my head here. Those particles, the relativistic particles can be independent of that. So this is a different type of solar phenomenon we call, not just the CME with the plasma, but the fast moving or slow moving solar wind streams. And that is something that's used, by the way, for lightning forecasting. So trying to get a really good understanding of that so that I don't communicate it improperly, like here, X'd out. True or false, some radiation storms contain gold. That really wowed me. Did you know that every single element on our periodic table, plus those that we have not yet discovered, are moving right through our bodies? that it all comes out of the sun in radiation storms, and even when it's not a full-blown radiation storm, there's still these particles leaving the sun and traveling toward us, and it will go through houses, it will go through our bodies, and people are trying to move to Mars, so perhaps scientists or anybody for that matter might come up with something that can block this stuff from affecting us so that we could have safe zones during, like, maybe there was a Carrington event that we all want to be prepared for on Earth. It's possible that we could probably come up with something that might block that, but I don't believe that we know anything yet, besides maybe very, very thick walls of some kind of a hard, dense material, like a thick rock, lava rock that's already here on Earth. So, can a four-bush decrease indicate that a solar storm is nearby? Yes. Yes. Galactic cosmic rays are observed to decrease as it interacts with the solar wind flowing with the CME. And darn, I don't remember what a four-bush decrease is, so I'm going to look that up real quick. Four-bush decrease is a rapid decrease in observed galactic cosmic ray intensity following a coronal mass ejection. It occurs due to the magnetic field of the plasma solar wind sweeping some of the galactic cosmic rays away from Earth. The term four-bush decrease was named after the American physicist Scott E. So here, along with the plasma ejections or a coronal mass ejection, there's the magnetic field of the solar wind. Now, galactic cosmic rays are separate and coming from outside our solar system, outside our heliosphere. So those can play off of one another. It sounds here then like the galactic cosmic rays sweep some of that other solar wind away. I'll have to think about that. Intuitively, I'm thinking that it probably connects magnetically in order to pull it away. Something I'll learn more about, I'm sure, because we just barely touched on that in my class last semester. And then we have coronal holes and sources of the solar wind. Coronal holes appear black at times, but again, like I was saying, some of the stuff can be bright in other wavelengths. So we're going to dig into that a lot here and why the solar wind is there. So true or false? This one's false, that the coronal holes appear dark on the solar surface in images 1600 angstroms and 304 angstroms of extra ultraviolet light. So no, those aren't the right ones. And we'll dig into that. There's some photos coming up here from the test to help explain that. Do coronal holes correspond to open or closed magnetic field regions on the sun? When magnetic field lines protrude away from the sun, so she says forming a looped field lines. I'm going to kind of, this is one I got wrong, right? So looped field lines are generally closed. Open field lines are the flowing outward, like that I was showing earlier with that outward flux from my past one. So to get this in my head properly, this is the open flux here. And so this one's going straight out. And I think with some things I've seen recently on the sun, there's actually huge sunspots facing Earth right now. So I've been reading more about this in real time with our current situation, trying to get a better hold of this. So she's saying that they're flowing outward, just like we saw. Open field line here, closed field line here. So the hole, this part's right then, the hole is really an area where some wavelengths are no longer emitting photons and can appear dark. Okay, so this is actually visible to our eye then in that case. The reason it appears dark on the sun, and you know what? Why don't I do this right now on the screen share? I can show space weather live because this is really an interesting situation right now with the sun. Here we go. Look at this puppy. It's very big. Normally they're not quite this big, and with this dark spot here, we have normally this one says that it's 500 kilometers per second with fast moving solar wind, which is about 50 to 100 kilometers per second faster than normal. Lightning and change radio communications in ways that I'm not quite ready to communicate yet, but this is pretty massive, and this is what we're talking about. Photons of light are clearly emitting here. Now, to our naked eye, it looks a little bit different, but we can actually see, people with high resolution cameras or telescopes can notice that this is dark looking, and it is because there's no photons being emitted. So interesting. And then to understand, okay, so that didn't open or close. Do coronal holes correspond to open or closed magnetic field regions on the sun? Looped fields. So these must be the open ones. The hole is really, okay, so that's an open field line. Yes. Those are fast-moving solar wind streams coming toward Earth with no loop. It's actually leaving the sun in that dark area and zooming right out to outer space, or in that case where it's facing us, and rotating onto that western limb. They're actually coming toward Earth. During the declining phase of the solar cycle, coronal holes are persistent over multiple regions, often having a wide extent and latitude. And this is so counterintuitive in my brain, thinking, okay, so now the solar cycle's on the, but what that means is that we're getting the coronal holes. That has to do with the solar dynamo reconfiguring inside. More for me to learn in that realm. But declining phase of the solar cycle, that short modern cycle, the 11 to 14 year cycle, as we're getting close to the end. We just hit solar cycle 25 about last year. Now we'll be going into solar cycle 26, but we're just at the beginning, so that's going to be about another decade from now. And we'll be able to tell scientists, they'll be able to kind of give us an idea of predicting when our solar cycle 25 is coming to an end by noticing that there's very long-term or coronal holes, like we just saw, where there's no light, no photons coming out, all over, persistent over multiple rotations, so they just stay there. It takes I want to say a couple weeks for the sun to go around a revolution. And in that time, if we keep seeing the same ones over and over in a wide extent and latitude, both not just like the poles like we saw in this case, but all over different spots that just hang out, we're reaching the end of a solar cycle. Now here we have a false. Coronal holes are not part of the coronal streamer belt. Those areas that do not emit photons. They have nothing to do with the streamer belt. Now here I'm labeling another diagram, and this is the heliospheric current sheet. Something that encompasses our entire solar system is the heliosphere. I just put up some really interesting information about that on my Weather Woman Facebook. You can look at how we just moved through a fold in this. So I kind of think of this as nucleuses of atoms, as though all of these planets and the sun, our star, and our solar system are all kind of being encased in this bubble of the heliosphere. And this current sheet has different points on it that can be positive or negative. You see here that there's negative charges and there's positive coming out, and things can flip. Everything's spinning and moving all the time, and things will reverse. We just went through a fold is what I shared. So different parts of this graph, things I just can't believe people have gone through the trouble to understand all this stuff. It's amazing to me. But here, labeling them, a magnetic neutral line on the sun is here. Oh, I see how Oh, she's asking on the sun. She says that's okay, but that's not it. So the magnetic neutral line would be this dashed line that then runs right in between this neutral stream outward. Thank you for giving me that. The heliospheric current sheet, the AKA, she calls it the ballerina skirt because of the way that it'll move around, kind of like a tutu, has all of these little wrinkles and crinkles, and I think of them as frequencies. You know how energy travels on waves; it's just always moving and rotating. So she kind of describes this as a ballerina skirt to help people visualize and conceptualize this. So that right there is the entire thing itself, and here we have this labeled as this outer rim. And then the ecliptic plane is this blue region. Now, that's where the Earth rotates around. All the planets rotate around the ecliptic plane, this circle, more of an ellipse, really. And the region of fast solar wind is popping off here in red. So here we have fast solar wind moving outward from the sun. And again, like those coronal holes, that can be a source of that, but not the only one from what I understand. One magnetic field line of the Parker spiral is right here. Some things shifted when I was saving this, clearly, and copied other places, but yeah, because I know that this is right here. A magnetic field line of the Parker spiral is those, all of these come out and into a circle as the sun is rotating, like we talked about. And if Earth is here, then this is our west limb right here, the parts that will, if they send something out and eject something, it will most quickly hit Earth coming from that region. An extra credit was the location of the coronal hole driving the region of fast solar wind, and that's the purple. So yes, it was the source region in this specific diagram, was one of those photonless coronal holes. 0 points. Okay, what did I do here? So, in the diagram above, why do the magnetic field lines converge in the compression region? So here we have slow, the sun is rotating here. We have fast moving solar wind. We have slow moving solar wind, slow moving solar wind. Wanting to say these have to do with, let's look at the real answer before I say something wrong. The field lines converge because fast solar wind spirals are less curved compared to slow solar wind spirals, so they collide. Okay, I can get this now. If something's moving slow, it's going to mostly be affected by the revolution of the sun. They're not as energized. They're going to drift and drift kind of slowly. If something's shooting out fast, we see these vectors here are indicating the speed, the velocity, by way of having a longer arrow here. So faster, faster. It's shooting out a little bit at a different angle because it's moving so fast, and so they bump into one another. And I suppose, yes, there we go. Slow and fast are hitting one another then. The fast is just kind of pushing into that, kind of like we do here on Earth to each other sometimes. So there we go. Things will converge when we have the fast-moving solar wind. We'll have convergence. And this is that copy and paste from the previous diagram. So yeah, we can ignore these things here. We have in the diagrams above, assume blue lines and negative signs correspond to north. So we have blue and negative as north. North polarity, north polarity. And then the reverse will be the south. So south and positive south. South magnetic polarity. That'd be a bipolar, by the way, dipole, like a dipole magnet does have two regions. There's different kinds of magnetic fields, but this is that positive, negative type. So a region, here we go. She wanted to know each one. In each diagram, label them. Oh, haha, so this one did need to get labeled, I guess. Cool. Here we go. A region of open magnetic field lines on the left. I wrote it out and did this because she wanted me to actually circle, but my printer didn't want to work for me, so that's why I did it this way. A region of open magnetic field lines is this dashed line. It's coming right out, whereas these are closed. And like we just reviewed earlier, this should also be an open field line. It's not looped going straight out. These are closed field lines connecting from a negative to a positive on the sun. And this is a much more simplistic diagram than what happens because you can see here there's some areas here in the center where you're getting crisscross, not quite from one hemisphere to the other. But this can happen on the same hemisphere, a north and a south. That's very common. So then on the right, it's the lines of the red. So the region of open magnetic field lines over here is going to be the red on top. Yeah, going straight out, not looping. Even these here would be open field lines. A region of closed magnetic field lines. Just went over that. So here we go. On the left, you see semicircles. And then I put that on the right. How funny, it came out like copyright. On the right, on the middle of the sun. These in the middle here are those closed regions where you can be on one hemisphere with both negative and positive connection, like we do see in real life often. A magnetic sector bound, or here, a helmet streamer or a coronal streamer is what's pointing to in purple. Coronal streamers here, part of the closed field line. A magnetic sector boundary, or the heliospheric current sheet, are these dashed lines and the dashed lines here, the streamers, streamer sheet. So that I have a lot more to learn about. It really interests me thinking about how these things can come from outside the heliosphere. Different particles and energies, maybe different elements that we have not yet discovered, could perhaps fall into that stream from outside of our solar system and affect us and change things on the planet, maybe speed up evolutionary processes, or give us new data to collect and understand something new, like name a new element for the periodic table. And now the magnetic north and magnetic south hemispheres of the sun. Looks like that should be, oh, here we go. The north is right here. Of course, she was saying the negative is the north, and that the positive was the south in this case, where south is indicated by red, and that can flip-flop sometimes from one type of diagram or device to another. And here we have what acronyms. What do the acronyms SIR and CIR stand for, and what's the difference between them, if any? Explain. The stream interaction regions and co-rotating interaction regions. She says, actually, a co-rotating interaction region is simply a stream interaction region that has survived a full solar rotation. Co-rotating, so nomenclature-wise, they're rotating. So I put that the difference is that HSS is interacting with the magnetic plasma in a rotation flow rather than a compressed stream. Co-rotating regions. Yeah, I still, this again isn't really intuitive for nomenclature purposes, so I misdiagnosed that answer. So we have then really these co-rotating regions are just a stream interaction region that has gone all the way around the sun and still exists. And that must be all of these streams outward then. Yeah, that's something I want to learn more about. I know this is the stream line to the heliosphere. technically called the heliospheric current sheet boundary. That's something I'm excited to dig into deeper, something we barely touched on there. So, true or false, this is going to be true. High speed streams, or HSS, can drive shock waves in space. High speed streams, they're moving faster than the other particles moving around that Parker spiral. You know how we saw things converging into each other when there's fast moving solar wind versus slow? Oh, if something's moving even faster than that, there's a high speed stream, it can kind of shock all of those other particles and drive out a shock wave that has different effects on moving the particles around it and in front of it. Now we have stream interaction regions and co-rotating interaction regions comprise a significant fraction of solar storms at Earth during the solar minimum. Solar minimum and solar maximum. I'll talk more about that. I don't think right now would be the best for that, since I don't have the visuals to go with that right now. The heliospheric current sheet is an extension of what solar feature into space? Heliospheric current sheet is, come to me, the magnetic equator neutral line. So that was that dashed line we saw between negatives and positives leaving the sun. From the Ulysses mission, we discovered the solar wind can do all of this. It varies at all, well, it varies from fast wind at high latitudes to slow wind at low latitudes. Okay, cool. I didn't know that. See, obviously I didn't get this one right. I thought only the last one here. So it varies, and now we're going to have faster solar wind at the higher latitudes toward the poles, and then toward the equator, slower solar wind. Interesting. Can't figure out why in my head yet, but I'm sure I'll figure out more about that. Also varies from low density and high latitudes. Hey, I knew this. Why didn't I get this right then? It varies. So there's lower density at the higher latitudes with faster solar wind. Then in those lower latitudes near the equator of the sun, we're looking at a high density with a slow solar wind. Oh, I see why I'm thinking low density. I think I reversed what that meant. So yeah, we're having something is fast, it's low density, there's not as much weight to it, it can move quicker. That happens near the poles, plugging this into my head now. Near the equator, we're going to have more dense material that slows it down and weighs it down, so that's a slow solar wind. And then this all can vary at all latitudes over the solar cycle. Why does the heliospheric current sheet form? The magnetic boundary, what magnetic boundary does it create? There is a magnetic neutral line streaming outward from the solar system. We've seen that dotted line coming out a few times now. It forms between the inward and outward magnetic field lines, respectively, connected with the southern and northern polarity of the sun. It is the spiraling of the magnetic field lines that form ribbons. Yeah, I see how that doesn't really apply to this question now, so I'll take what she underlined here for that. Now here we have a true. The slow solar wind comes from coronal streamers and embeds the heliospheric current sheet. The breathing heliosphere and the solar activity cycle. This is false that higher sunspot number cycles typically correlate with longer cycles. So I'm not sure if that is kind of null and void or if it's actually the reverse, that there's lower, but we don't need to correlate solar cycle length, that 11 to 14 years, on how many sunspots there are. The 11-year solar activity cycle can be observed using any of these. the frequency 10.7 radio flux, TSI solar flux, sunspot number, galactic cosmic ray flux. So all of those have influence on it. Now here, this is false, that the most extreme space weather events typically occur during large activity cycles. It's actually, the way I like to think of this, is somebody who bottles up a lot of emotion or anger. They're typically someone who might just take it all day, and then freak out. I kind of thought of it as like an explosion, like of anger, like that. But really, then in terms of the sun, we're looking at if there are not a lot of, here's another one for earthquakes. If there aren't a lot of small tremors, if we're not getting a lot of 4.7s, a lot of 3 points or 5 points, and a lot of time goes by, oftentimes we'll notice that there's that big old 9. So these buildups, if there's less activity on the sun, and it's not a lot, well, then some scientists get a little worried that, are we going to have a Carrington event on the sun, a big, huge, massive, energetic ejection from the sun, because it has kind of bottled up for so long that when it finally lets go of what's inside underneath that dynamo, it's explosive rather than little short bursts here and there. And I think of that too as natural cycles. It seems like a lot of natural cycles like to try and attempt to reach equilibrium, like how we transfer energy during hurricanes toward the poles. And in those years where there's a lot of that, the poles also transfer a lot of cold back down. And we'll see our long wave patterns in the atmosphere more extensive, a higher frequency on those years, whereas it might be a little more mellow on years where there were just a few hurricanes going up. Then there's just a few pushbacks of the. And so, double peak and sunspot number during a solar activity cycle is indicative of a asymmetry between the stars. I'm trying to remember what this means. A double peak. Oh, I remember now. There was a graphical representation of this. That if we're looking at on a timeline, there's 2 peaks on a sunspot where it's really intense during a solar activity cycle. It means that there's asymmetry between the sun's magnetic hemispheres. A little hard to interpret that for somebody who might not know what that means without visuals, so I'll move on from that one for now. Then we have, which of the following is true when the sun is most active, near or at solar maximum? Radiation storms strengthen, but cosmic rays are at the lowest flux intensity. So when the sun is most active, getting close to a solar maximum, or at solar maximum, radiation storms, all those high energetic protons coming toward Earth, they can strengthen and increase, but the cosmic rays, the galactic cosmic rays coming from outside of our solar system, are lower. They kind of play off one another, and right now we're kind of on a downtrend of the sun activity, and for that reason we're seeing more galactic cosmic rays coming in toward our solar system and toward Earth. And here we have a true. The 11-year cycle is only one of many activity cycles of the sun on different time scales. Oh, well, yeah, I knew that. How in the world did I think I read like that the 11-year cycle is the only one, and I was like, false. But yeah, I know that. I already mentioned, there's plenty of solar cycles. What a bummer. This was like, by the way, it took me 15 hours to finish this long test. So that was probably me at the end. But here we have another 0 point. So this is number C, or letter C. New cycle sunspots indicating the start of a solar cycle first appear at high latitudes near the solar minimum. Yeah, I remember that now. So I wonder, I kept kind of reversing minimums and maximums. So I'm going to nail this one in my head right now again. That when we have a new solar cycle, sunspots with that different polarity, like I was saying, for the most part, because of Hale's law, we'll see that there's a negative and a positive On the left side, it'll be negative. On the right side, it'll be positive, let's say, on the northern hemisphere. But when that solar cycle is changing, that will reverse. And that the reversal first occurs higher up in latitude, closer to the polar region of the sun. In the diagram above, we're labeling again. So, hey, the sun, who knows where that is? It's at the center of our solar system. That was easy. It's very big, bright and yellow for the most part to our naked eye. So there we go, the termination shock. Now we're talking about shock waves. And this is where the shock wave terminates. Looks like this line is a little bit funky. Oh no, here, yeah, good, perfect. It's right at the outside of this bubble here. We have where the shock wave stops. The polar magnetic field spirals. These come off at both sides with different polarities. So here we go. She calls them waffle cones to kind of give people an idea of the design and the structure of this shape. And something that was interesting to me is that these can go kind of be accepting. Things will change at different times of the cycle, and right now we're in a portion more like this where we can accept more from outside of our heliosphere, from outside, deep out into space, because these the way that these are oriented can allow different particles to float in toward here. And then we have the leading edge, or the bow of the heliosphere. Kind of, you think of a bow shock, or that's going to be right here. That there's a shock stops here, but then the bow that's created ahead of it's there. A lot of research that's been done on how things travel in space. Objects that don't necessarily use the rules we do for our cars and our vehicles to operate and propel. If something wants to move through space, it will just displace what's ahead of it. And this bow shock helps displace what's ahead of the termination shock and allows us to continue moving through space. So that displacement, and you see how it's kind of a circle. It allows it to move this way. So yeah, this arrow, technically, I guess if I want to re-examine this, I'd probably put it more here on the critical point of this curve and say that this is moving here. Now the bow shock is all the way out here. The shock from that bowing then has its own shock out ahead of that you can see will have different interactions with what it is displacing, what it's interacting with, because then we have things from our planet, our solar system, our sun, and what's in between. They're interacting with outer space, outside of our heliosphere. Now, to indicate with an arrow the direction of the heliosphere, that's this right here showing. So this is how it's moving through the intergalactic flow outside our galaxy. Can you see why this test took me so long? Gosh, I'm already tired again. Almost done. I just love this image. I'll make sure my face isn't over it. This is our heliospheric current sheet, that ballerina skirt. These are those waffle cones that at this point are very much well defined like this, allowing particles to travel in toward our solar system from outside of our heliosphere. I can't wait to learn more about this. It's so trippy to me. So label the HCS, the heliospheric current sheet, and the polar magnetic fields in the above diagram. Do galactic cosmic ray particles enter the heliosphere more readily through the heliospheric current sheet or through the spiral fields in the polar regions? Explain. And I say that by labeling them. The blue in this case is the southern magnetic field, the South Pole, and then the red is the north. Now, north is moving away. Gosh, I'm so not used to this program with this update. I hadn't used it in ages. So what's happening here then, something that I want to remember because it kind of wasn't embedded in me when I was sharing this earlier, that magnetic field lines are moving toward the sun with the south polarity coming in, and this is going outward. I always thought of this like a high ways for me to kind of conceptualize this and bury it in my head here. We have with weather, everything wants to flow from the high pressure to the low pressure. Here we have an electric flow, so we're going the south toward, and away is the north. So I kind of, over time here, I'm relating this to my meteorology studies, and I'll keep interpreting that in different ways of how things are connecting and the flow directions. Because I think a lot could be said about that with what we have available to be learning about our magnetosphere and magnetics as a whole. How we could propel using them. I kind of feel like it's more of a geothermal process. In some ways, of course, this is not geo, this is from outer space, not from our globe. So a lot to learn to interpret. Now the purple, like I said then, was that heliosphere current sheet. So to reiterate what this means here, do galactic cosmic ray particles enter the heliosphere more readily through the heliosphere current sheet or through these spiral fields? And like I had mentioned earlier, the spiraling regions are more open to the galactic cosmic rays compared to the more organized field lines of this heliosphere current sheet. Because these field lines are open, that's why it's so accepting. It's kind of like, hey, come to me, and the rest of it's like up and down, kind of perpendicular to that intergalactic flow or the galactic cosmic rays. Instead, heliosphere current sheet will hit like this with the GCRs, and then the waffle cone area toward the poles, it's just like, hey, come on, buddy. Now, which solar minimum was deeper than the infamous Maunder minimum? The late medieval minimum. So these Maunder minimums are Maunder minimum. There's a lot of different solar cycles, minimums and maximums that we went over. And then when I go to edit, I'll add some of that on top of here so you can actually see just how intense they were and when they occurred. But we had a very crazy minimum with the late medieval period when I think it's the Times River froze over. I just barely learned about that, but I do know there were wildly cold temperatures in this time period some 100 years ago, just a few 100 years ago, about 4. Now, true or false, and I believe that's a 200-year period, so we had a Maunder minimum, and then before that, a medieval minimum that was more intense. So here's a true. The current solar cycle is a cycle that has a high probability of producing extreme space weather events, such as the Carrington class event. And that, again, is because we're not seeing a lot of activity on the sun right now. It's not giving a lot of bursts. It's kind of quiet, they call it. And therefore, it's building up. It's building up. And when it does release, let's hope that that big old bad burst is facing away or on that east limb of the sun at least, so that it does not really impact our magnetic field as much as it could if it was facing us in that center of the plasma ejection and solar activity, high energized particles. It'd be nice if they don't come ruin a bunch of things on Earth. Like just to put in there, the Carrington class event that was observed in the 1800s did end up having enough energy that got into our ground on Earth that it got to grounded wires. And then from that, these energy bursts, that actually particles of energy traveled up through these grounded wires and ended up being so energized that our machines, like the telegraphs at the time being used, we're not ready to push back that kind of a power. We hadn't really even understood that that was possible, and then therefore equipment malfunctioned and people were physically burned. Some things lit up into fire, and then I've learned that transformers. I have more to learn about this, but when there's moisture inside of our systems producing energy to flow to our homes, some of these systems are a little old, and I've been told the moisture inside there can also be a catalyst for some bad reactions where things will spark. And I know that salt, how do I put this? Salt sparks electricity. So perhaps there's salt in that water too, and some of that can be even more powerful than to actually have a chemical reaction that will produce a flame. Now we have, but don't fear, by the way. I know a lot of people are so scared of that stuff. Just go with it, and we'll just keep on learning. And I feel like living in fear is more counterproductive than just realizing that all of this could end at any moment anyway. And the likelihood of that being in our time period is so slim that I'd rather just kind of focus on developing and further studying this information so that we can mitigate it before the events happen. And when these events do happen, like the Carrington class event, I don't believe there were deaths involved. And then there's a lot of movies that are very doomsday and saying that we're all going to die from this stuff. I don't believe that has to be the case, and there's so many people studying this right now that we're learning more and more ways to mitigate it. So just keep enjoying your life, regardless of that things like this can happen out of nowhere. Now, the Schwab cycle is often referred to as a 22-year cycle. Why? Is that a correct assessment? Why or why not? So the magnetic field of the sun changes from a bipolar to a multipolar field about every 11 years. Then it will go back to a bipolar field in about another 11 years. It can be deduced that an average of 22 years passes between the time periods where the field orientation is the same. However, it is not concluded as a 22-year cycle in any of the academic publications I have viewed. So, unfortunately, I hate typos so much. But yeah, I was tired 15 hours working on this. Basically, our Maunder cycle is 11 years, but for the complete reversal of that bipolar field to come back to a bipolar field after being a toroidal field where things might be everywhere on the sun, things are connecting magnetically positive to negative all over the place, and then things will get an axial field line at another 11-year period, and we'll have more negative, more positive on one side or the other. Then 22, be connecting like this a lot. 22 years later, it'll be upside down. But in that in-between time, it's everywhere. And so our solar cycles are actually deduced as being when is it going from a bipolar field to a toroidal field? Done. Solar cycle over. Then we go back and flip again, upside down, and then toroidal, back to the other way. Now the last one gets a little fun. I wonder if I should even add it in here. But I will, I guess. Yeah, why not? For completedness. Considering we didn't get a chance to go over the trailers in class, nice job, she says. Yeah, so I'm glad I got these all right because, like she says, we didn't review all of this, and I just kind of went with my gut here. Consider the images shown above. All but 4 are from the current COVID-19 pandemic response, which I could say a lot about, but I won't right now. Can you label the 4 that came from the Blackout series trailer? And so, as we discussed in class, what are some similarities and differences between the impact on society of the current COVID-19 global pandemic and that from a possible extreme space weather event like the Carrington class event of 1972? If it were to hit Earth in our modern era, you might write from any perspective. And just so you have a heads up, that 1972 Carrington class event did not bother us because, like I was saying earlier, had that 50% chance that the polarities were not such that they would connect with Earth's magnetosphere. So it blasted by us, but didn't bother us like that one from the 1800s I mentioned where people were burned. So here, I mean, I guess it was pretty obvious to me. Oh wow, that's a good one. That most which ones were from the trailer and which weren't. But I'm glad to see this because people were being arrested. So I thought I kind of figured I didn't go open the trailer and find it. I kind of looked for it in our class stuff, our documents, but I didn't find them. And I know people were being arrested during the COVID crud, but in fact, all but four are from the current COVID 19. Can you label the four that come from the Blackout series? From a trailer, from a movie? Gosh. Dang. It's hard for me to wrap my head around this. I didn't notice this when I reviewed this first. This is the first time I'm really going over in depth. This is from the COVID 19. This is insane to me. People are being treated like this over a virus. Knowing what I know about being healthy and taking care of our own bodies and immune systems just by eating properly. I have had a lot of hospitalizations in my life, and I'm totally healthy now. Really on the up and up. So happy, and it's all completely because of my diet changes, my extreme diet changes, making sure I'm juicing. And I have theories that what we're growing, what's grown locally, it has the same. Those plants, I feel like they're being built up with the same intake from the sun and outer space as our bodies, and that they're being produced with those same changes. It's hard for me to articulate all this stuff because it's new to me, but I bounce these ideas off of people in the medical field, and I'm getting similar feedback, and nutritionists too, that some of this makes sense. When I have conversations with them, they know the proper words to use. But I really believe that going and taking medication with all of the other input, it only gets copyrighted because it's being used from a natural source like our plants and our food. And then it gets a trademark on it. It can be sold as a pharmaceutical once there's man-made materials inside of it. But if I just go directly to the source and get like parsley or cilantro grown from where I am, where my body physically is, then we are all taking in the same amount of particles from the sun, from outer space, and the galactic cosmic rays. It's kind of being built up to help me too. And when I input that into my body and notice that those couple of herbs are heavy metal binders, it can travel through my entire body, through my brain, and excrete some things that might not be so good for my body. I've noticed drastic changes in my health. And so to see that all these people being arrested is actually from these modern days and not from a movie is pretty sad to me, because there's no way to escape viruses. And even the manufacturers of the masks, I know somebody did a study on them. They state that the level 1 masks don't protect against anything. And the vaccine manufacturers for COVID state that it does not protect against COVID. So there's a lot of information that's not being vocalized and broadcast at large that could really change people's health. And so I hope more people learn how to just eat properly, and that people can stop arresting others because they wanted to live their life and catch a virus if they feel like it, and probably be asymptomatic as long as they're taking care of their body. So here, after that rant, these are all from a movie then. Here we go. Movie. The sun doesn't quite fire off that many at one time, this large. We have a movie here, Shelter in Place, but that could have been from from this current situation as well. So this one was an X. Oh yeah, I should have known. So they're saying that coronavirus is named coronavirus because it looks like the sun. Gosh, how weird that that is not from a trailer, and that's like, whatever. Moving on to the answer here, then. She has wanted to know then what are some similarities and differences between the impact on society between COVID-19 pandemic and something like a Carrington class event. And this would be Astro Sociology, like I was talking about. So I say because we have more ground wire and digital machines throughout our infrastructure, I believe a modern day superstorm would send shockwaves throughout society, more drastic than it did during the 1800s Carrington class event. From direct events, from direct effects such as ground wires overflowing with particles, to indirect effects such as new fields of study being developed to mitigate unexpected consequences. So as a result of something like that, yeah, I do believe people would say, "Uh-oh, we got to learn more," and that they'll have complete new agencies around the world investigating this stuff on how to mitigate it and how to prepare for it. And then a difference. One of the differences would be that the masses of people would turn to space techs for the answers, whereas medical professionals are more connected to biological viruses. But unfortunately, a lot of their voices are being quieted if they're not on the scare tactic side of things. So I hope that with space weather, we can see something different come out of this. Similarly, some would be scared and some would seek new information. Others commit suicide or maybe become mole women, like on Unbreakable. If you haven't seen that Netflix show, my goodness. Yeah, so I can imagine, some people would want to run and hide if a Carrington class event occurred and just say, I'm never going to see the sun again because what can it do to me? And then other people are going to say, hey, let's find out how to become one with this and continue living. And she wants a little more depth in the answer, though. So, probably some of what I added in and ranted about would have been helpful to put in there then for her. It was called a short essay question, and maybe I went a little too short then, but still got my point, so that's nice. And then this part, I hate the idea of bashing someone I have never met in person, but I'll go ahead and read these anyway because what she asks is for positives and negatives here, but I'll still put it out there anyway. And then no hate to the person. I've never met him in person, by the way, so I'll just move on with this. Name one pop culture icon or celebrity who you think has had a has positively influenced public appreciation of space and space weather culture. Why? So I chose LeVar Burton of Reading Rainbow because he held my attention as a child and I appreciated all the things that, were of science since I was a child. And I loved the way he shared. I loved that he gave us visuals and he would go meet with people in laboratories and show the specifics. Really, really easy to understand and follow what was going on. And I'm a huge fan of that show and the work he did. And then she wants to know a pop culture icon or celebrity who I think has negatively influenced public appreciation of space and space weather culture and why. And I chose that I have been concerned with quite a few comments made by Neil deGrasse Tyson, most specifically the wording used in his advertisements. This is pretty recent now. The promises made appeared fruitless and far-fetched with a lot of illogical rhetoric and in the scripting. It seemed like it was more of a moneymaker and that, again, like kind of scare tactics to get people to, sign up and pay for stuff, and that the details being told, the promises being made, they didn't sound like things that were true. This has happened time and time again, and I noticed a lot of people in the comments because some of these are like on social media platforms, and other people will make mention of the same stuff that I don't really think that you're describing this process quite right. And a lot of that too has to do with climate change, and there's a lot that could be said about that I think that the mainstream media, uh, general population, I don't think that they are grasping the true effects of why our climate changes. And I think a lot of it has a lot more to do with the solar cycles, those long-term solar cycles too, and that it's easy to take advantage of people during those times where things are changing rapidly to grab money and to scare them into saying, yeah, give me money and I'll fix this, or carbon taxes. And but really, I don't believe that carbon is the main driver for a reason that climate would change to begin with. And quite a few other professionals and academics, professors have agreed with that. And I've grilled them all that I can come into contact with, and 9 times out of 10 they say, no, I don't believe that. But we're hearing the exact opposite, that 99% of scientists agree that climate change is all anthropogenic and caused by people, and I cannot side with that whatsoever. And from my own research and knowledge, that is not true. So here I did want to put a disclaimer here because, like I said, I haven't met these people. So I said it appears my age and information received is the only discrete discriminator between the pro and the con here, with the two, the positive and the negative. Perhaps my inspiration from the former was just as negatively received by a then academic mind. I believe no matter what we do, we are subject to error. But I do feel I receive more proof and better interviews via reading Rainbow in contrast to the work I have watched by Neil deGrasse Tyson. And that is how it is. So no hate on to him, but yeah, I do believe that it's an interesting subject material, and people want to know about physics. They want to know about weather. They want to know what is going to affect them, geomagnetic storms, and it's all so new. And I'll end on this note since it got a little, uh, let's say, how do we put that again? Astro Sociological here. That I heard recently a scientist who was being interviewed, and he had been talked down about a lot. He had been told he was a liar by a lot of people, and now his proofs are coming out. Documents are being unsealed. What were once confidential documents are now being revealed, and people are realizing, okay, he wasn't lying to me then. These far-fetched ideas, these things like I was telling about how things drive through space by moving the field in front of them. Yes, things can fly through space. It's not well known, but he said that it is the suppression of science, the suppression of the science we don't know, that he thinks is the most damaging to us. That I have seen this in my own line of work and throughout society, that if we don't know something, a lot of people have they have the kind of they go straight to quieting it. If we don't have all the answers, they say, don't put it out there. And I believe a lot of that cause, especially when it comes from the government, can really be because if we give out some parts of information about, like, yes, we can drive through space, someone else might go and use that, learn more about it, experiment it, and then use it against the general population. And there are certain entities and agencies with more money, like the government, that say, hey, we better protect ourselves and make sure we know all of this, suppress the science, suppress that these things can actually happen, in an effort to be the first ones to know how to control it. How to then, if somebody were to use it against them, they can say, oh, well, I already see you on a radar beam, so I know you're there, I know you're trying to do this, and I have a way to stop you from doing it. And so there can be reasons, there can be pros to suppressing unknown science, but as a whole, it stunts the scientific community from expanding. And so I was on the side of that scientist who was being interviewed, who wanted to speak out and share. I didn't quite think should be sealed information. And that's very debatable whether or not, that should be the case or not, to suppress certain scientific topics, like I just kind of explained how someone could then use it against you. So I am definitely on the wavelength, though, of thinking that we should probably share more of this than we hide. And, that's debatable. So no worries if you think otherwise. Please don't hate on me for thinking the way I do. And if you do, oh well, we're good. I'm good on this test. I'm glad I got an A. If you guys have any questions, please put them in the comments. I'm happy to keep communicating this and explaining it as much as I can, because it helps me then as a broadcaster get the wording right. Make sure that it's in terms that people can understand who don't spend hours studying this kind of stuff, because sometimes the words can get large. And also, what I love is hearing other people's explanations on how this stuff can affect us. There's different types of things like that I've learned as a meteorologist. I might be talking about convergence of flow, topographical flow, how air masses will push together and create upward motion if there's two mountains next to each other and then open water. But people who sail might have other terms that they use for those informations. And so I love hearing other people's descriptions. So please load up the comments with anything about that, how you interpret some of this information, or different connections you might notice from mechanics or any other sources, because this is all about electrical flow. It's a lot about mm, what else can I don't know all my wording yet here, so I'm just going to keep learning. And yeah, if you see anything related, please go ahead and put it down below and ask questions as much as you feel like. So thanks for joining me. If you found this interesting, and a lot of people don't care to look at all this, so no worries if it was just for myself. Have a great day. I'll keep researching and learning ways that we can better our forecast models for weather here on Earth is my main goal here. Have a nice day and enjoy the weather. This is your weather woman, meteorologist Amy Metz.